You take a cold plate of leftovers from the fridge. You place it inside a small metal box on your kitchen counter. The door shuts. You press a single button, and 2 minutes later, you pull out a steaming hot meal. For most of human history, cooking required gathering fuel, striking a spark, and managing a physical fire. Then, suddenly, we could achieve the exact same result with the press of a button. But if you stop to think about the physics of that box, the process seems impossible. There is no open flame inside. There are no glowing heating elements. Even the air remains completely cold. So if the box itself does not produce any actual heat, where is that intense thermal energy coming from? The microwave waves force the food to generate its own heat from the inside out, turning the meal itself into the source of the thermal energy. To see how it does this, we have to look behind the keypad to a specialized component called a magnetron. This diagram shows what that part does. The magnetron takes standard household electricity and converts it into invisible electromagnetic waves. These waves flood the metal box, bouncing endlessly off the internal walls and converging directly into the center of your food. The waves blanket the entire chamber, but they completely ignore the air, the glass plate, and your ceramic bowl. They are hunting down a very specific molecular target. That target is water. Almost everything we eat contains trapped moisture, even foods that feel completely dry, like a piece of bread or a raw potato. If we plunge past the visible surface of that potato and enter the microscopic realm, we find tiny droplets of water hidden throughout its structure. Break one of those tiny droplets down even further, and you will find it is composed of millions of individual water molecules. If we look at a single water molecule, it has a distinct structural trait. One side carries a positive charge, and the other side carries a negative charge. It functions exactly like a microscopic magnet. This tiny, polarized magnetic structure is the hidden engine that powers the entire cooking process. When invisible microwave energy washes over that water molecule, the positive and negative poles react, forcing it to physically flip around to align with the changing energy. This is an incredibly violent reaction. The waves force the molecule to change directions millions of times a second. Remember, there are millions of these molecules packed tightly in a single drop of water, all frantically flipping at this exact speed. They crash into each other, they scrape, they bounce. All of these continuous microscopic collisions create intense friction, which generates kinetic energy. We experience that invisible kinetic friction as physical, localized heat. This is why a bowl of soup, which is full of millions of violently crashing water molecules, gets extremely hot, while a dry cracker, which lacks those molecules, barely warms up at all. The microwave cooks food through this friction, forcing water molecules to violently rub against one another millions of times per second. Zooming back out to human scale, we see exactly why microwaving food can be so frustrating. Because heat is only generated where water exists, the heating process is inherently chaotic. The microwave energy inside the chamber is not uniform. The spinning glass plate exists to rotate your food through different energy zones, preventing specific spots from being constantly bombarded while others are completely ignored. But the food itself is also even. Pockets with high moisture will rapidly boil, while denser, drier areas a few inches away will remain ice cold. This cross-section shows why standing time is so important. By waiting 1 to 2 minutes after the microwave stops, you allow the localized boiling hot pockets to safely conduct their thermal energy into the surrounding cold pockets. Following the instructions on a frozen meal, stirring halfway through, letting it rest, is not optional advice. You are manually managing the localized thermodynamics of your dinner. This microscopic physical reaction also explains the dangers of the appliance. When microwaves hit materials that lack polarized water molecules, like metal, they bounce right off. Smooth metal safely reflects waves, but sharp edges, like the tines of a fork, concentrate the energy into a violent electrical charge, creating destructive sparks. The water itself can also be a hazard. When molecular friction boils liquid water into a gas, that rapidly expanding steam requires physical space. If you trap that expanding steam inside a sealed plastic container, a tight hot dog skin, or an eggshell, the pressure builds until the food turns into a pressurized microscopic bomb. Pressing the start button sets billions of tiny water molecules into a blindingly fast dance, generating the heat needed to cook your dinner from the inside out.